2.6 Lesson 1, the intermediate value theorem and its consequences. We have 3 objectives for today. Objective 1, you'll understand when the intermediate value theorem can be used. So what is the intermediate value theorem? We will look at that. It is stated as a conditional statement. There is a hypothesis, and basically when you have the hypothesis satisfied, then the conclusion must follow. So when can you use the intermediate value theorem? When you have a problem in which the hypothesis is satisfied. So let's take a look at the second objective. You will understand what the intermediate value theorem states. So we will look at the intermediate value theorem, and it states that whenever the hypothesis is satisfied, the conclusion must be true. So we'll look at the theorem and you'll see what that means in the context of the theorem. And then objective 3, you'll be able to use the intermediate value theorem to determine that a function has at least one zero on a given interval of x values. So what is the intermediate value theorem? We've learned about continuity before, and there is a concept from algebra, a zero of a function. So for example, if you have f of x is equal to x squared minus 4. What are the zeros of this function? The zeros of this function are the x values that will make the output values of the function equal to 0. So to find the zeros, you can set the output value of the function equal to 0 and solve for x. So when you solve this equation for x, you get x squared is equal to 4. So x could be either positive 2 or negative 2. These are called the zeros of the function. And again, zeros of a function are input values that would make the output equal to 0. So the input values that make the output values equal to 0 for this particular function are positive 2 and negative 2. They correspond to the x-intercepts of the graph of this function, because what you have here are the ordered pairs 2, 0 and negative 2, 0. So the zeros of a function correspond to x-intercepts of the graph of the function. So the zeros of this function are positive 2 and negative 2, and the graph has two x-intercepts at 2, 0 and negative 2, 0. So here we have the intermediate value theorem. It is a conditional statement. We have if, then. If the function f is continuous for all x in the closed interval ab, and y is a number between f of a and f of b. So these are called the hypotheses of the theorem. In other words, if these things that I underlined in green are true, then there is a number x is equal to c in AB for which f of c is equal to y. That's called the conclusion of the theorem. And what you have here is a conditional statement. And of course, this is the intermediate value theorem. So we just looked at the intermediate value theorem. It is a conditional statement. It has hypotheses and a conclusion. And in the hypothesis, one of the conditions is continuity. So when can the intermediate value theorem be used? And what does it tell us? The intermediate value theorem can be used when you have a problem that satisfies the hypotheses in the theorem, and it tells us what the conclusion states. Let's see if we can list the hypotheses of the intermediate value theorem. If the function f is continuous for all x in the closed interval a to b, and y is a number between f of a and f of b, what does it mean to say that y is a number between f of a and f of b? Well, the function is named f, and a and b are input values for the function. So f of a is an output value from the function, and f of b is an output value from the function. So y is a number between f of a and f of b could mean that you have y is greater than f of a and less than f of b, or it could be that y is greater than f of b and less than f of a. So whatever f of a and f of b may be, you have a y that's between f of a and f of b. So if these three conditions are satisfied, then the intermediate value theorem applies. And it states the following. Then there is a number x is equal to c between a and b for which the function's output at c will be equal to y. So again, the conclusion would be that there exists an input value c where c is between a and b such that the function f evaluated at c will be equal to y, and this y is the same y that was mentioned in the hypotheses. So let's take a look at an example here. So again, here we have the intermediate value theorem. The hypotheses are you have a function f that is continuous for all x in the closed interval from a to b. So in our example, our function is f of x is equal to x squared minus 2. This is a polynomial function. You can see the graph is a parabola, and in fact, this polynomial function is continuous for all real numbers. So it is continuous on the entire real line. Let's go ahead and consider a particular interval for x, from x is equal to 2 to x is equal to 3. So on the interval from x is equal to 2 to 3, the function f is continuous because it is continuous everywhere. So we have a function that is continuous for all x in the closed interval from 2 to 3. Now what is f of 2? Well, that's easy to figure out. You just evaluate the function f when x is equal to 2. So you'd have 2 squared, which is 4, and 4 minus 2 would be 2. F of 2 is equal to 2. What is f of 3? F of 3 would be equal to 3 squared, which is 9. 9 minus 2 is 7. F of 3 is equal to 7. So suppose I choose a number that's between 2 and 7, maybe 5. So maybe I choose y to be equal to 5. Then it is true that 5 is between f of 2 and f of 7. I'm sorry, between f of 2 and f of 3, which is equal to 7. So look at this. So now we have a y value that is, and you have a y value if it's between f of a and f of b. So I have a y value that I chose, or it could be given to you in a problem, and as long as that y value is between f of a and f of b, in our case f of 2 and f of 3, which are respectively 2 and 7, and 5 is between 2 and 7, then we have the hypotheses of the intermediate value theorem satisfied, which state that you have a function f that is continuous for all x in the closed interval from a to b. We have that, and we have a y value, 5, that is between f of a and f of b. That is between f of 2, which is 2, and f of 3, which is 7. So we have the hypotheses of the intermediate value theorem satisfied for this problem. Then what does the intermediate value theorem tell us? It tells us then there is a number x is equal to c between a and b, between 2, and 3, for which the function evaluated at c will be equal to y. In our case, y is 5. So there is an input value between 2 and 3 at which the output value will be equal to 5. That's all the intermediate value theorem states. It's called an existence theorem. It doesn't really tell you how to find that particular input value. It just tells you that because the conditions from the hypotheses are satisfied, there must be at least one input value between 2 and 3 for which the output will be 5. It tells you that there is such a value. It's an existence theorem, but it doesn't really tell you how to find it. So let's recap what we just talked about. In this particular problem, the intermediate value theorem applies because the hypotheses are satisfied. We have a function f that is continuous on the entire real line, and therefore it is also continuous on the interval from 2 to 3. And we have a y value that is between f of 2 and f of 3. 5 is between 2 and 7. So the hypotheses of the intermediate value theorem are satisfied, so the conclusion applies. And it tells us, it gives us a guarantee. It guarantees that there must be an input value between 2 and 3 at which the output value will be equal to 5. It doesn't really tell us how to find it, but of course we can find it by using, for example, Desmos or just doing algebra. So if you wanted to find an input value between 2 and 3 at which the output is equal to 5, you could do it simply by graphing the line y is equal to 5 and seeing where that line intercepts the graph of f of x. So here's the line y is equal to 5. And you want to see what is the x value between 2 and 3. So here's 2 and 3. What is the x value between 2 and 3 at which the line y is equal to 5 will intercept the graph of f? So you can find the coordinates of this point of intersection, and that would tell you the input value between 2 and 3 for which the output of the function will be equal to 5. And you can see that I've done that here. I've graphed the horizontal line y is equal to 5, and I used Desmos to find the coordinates of the point of intersection between the horizontal line y is equal to 5 and the graph of f. And that point of intersection has an x coordinate of 2.646, and you will see that this x coordinate of 2.646 is between 2 and 3. It is between A and B, between 2 and 3. 2.646 is between 2 and 3, and that's what the theorem is telling us. There is an input value between A and B for which the output must be 5. And that's exactly what we found using Desmos. You could also find that value of c guaranteed by the intermediate value theorem by setting your function equal to 5 and solving for x. If you were to do that, you would add 2 to both sides of the equation, giving you x squared is equal to 7, and then you would take the positive square root of 7 because we want to find an x value between positive 2 and positive 3 such that the y value will be 5. So you would take the positive square root of 7, and that would give you 2.646, approximately 2.646. So when can the intermediate value theorem be used? It can be used when you have a function that satisfies the hypotheses of the theorem. You have a function that's continuous on a closed interval AB, and we're looking at a y value that's between f of A and f of B. what does the intermediate value theorem state? It states the existence of an input value c between a and b such that the output value of the function at c will be equal to y. We saw an example of the application of the intermediate value theorem just now. Now we will take a look at a second example for objective 3, which is also applying the intermediate value theorem. You will be able to use the intermediate value theorem to determine that a function has at least one zero on a given interval of x values. So when you take a look at the graph of f of x is equal to x squared minus 4, you can see that this particular function has two zeros, one at negative 2 and one at positive 2. So when you use the intermediate value theorem to determine whether a function must have a zero on a given interval of x values, you want to choose two x values such that at one x value the output will be a negative value, and at another x value the output of the function will be a positive number. So between a negative number and a positive number must be zero, and basically that's the idea with using the intermediate value theorem for objective 3. You will be able to use the intermediate value theorem to determine that a function has at least one zero on a given interval of x values. So you want to choose an interval of x values so that the output value of the function at a will be negative or positive, and the output value of the function at b would have the opposite sign. So that zero would have to be between those two values, and therefore by the intermediate value theorem there must be an input value between a and b at which the output must be zero, guaranteeing that the function has at least one zero on the given interval of x values. So now we go back to the same function that we were looking at before, but we're going to change our interval for x values that we look at. We're going to look at the interval from x is equal to 1 to x is equal to 2. Because at x is equal to 1, the output is a negative value, and at x is equal to 2, the output is a positive value. And between this negative and positive number, we have 0. So let's list the hypotheses of the theorem. We have a function f that is continuous for all x in the closed interval from 1 to 2. The y value in our problem is 0, and y is a number between f of a and f of b. F of 1 is negative 1, f of 2 is positive 2, and 0 is between negative 1 and positive 2. So what does the intermediate value theorem tells us? It is an existence theorem, so it makes a guarantee. It guarantees that there must be an input value between 1 and 2 such that the output of the function will be equal to 0. So in this particular problem, we are able to know, using the intermediate value theorem, the existence of a 0 for this particular function. And that 0 must be between x is equal to 1 and x is equal to 2. And that is what objective 3 is all about. You'll be able to use the intermediate value theorem to determine that a function has at least one 0 on a given interval of x values. So the intermediate value theorem guarantees the existence of a 0 for our function, but it doesn't tell us what that 0 is. If you wanted to find that 0, you could find that algebraically, or you could find it graphically. To find it graphically, you would graph the horizontal line, y is equal to 0, as I'm showing you now in gold. And then you would find the intersection of y is equal to 0 with the graph of f between x is equal to 1 and x is equal to 2. And that point of intersection would be right here. And the x-coordinate of that point of intersection will, of course, be between 1 and 2, as guaranteed by the intermediate value theorem, that there is an input value c between a and b, between 1 and 2, such that the output of the function will be equal to 0. And you can see here that I've found that particular value at which the function will be 0 by using Desmos. I graphed the horizontal line y is equal to 0 and found the coordinates of the point of intersection between y is equal to 0 and the graph of f. And the input value between 1 and 2 at which the function will have a 0, as guaranteed by the intermediate value theorem, is about 1.414. X is approximately 1.414. Can you find this algebraically? Yes. To find it algebraically, you would just set the function f of x equal to 0 and solve for x. So you get x squared is equal to 2. And because you're only looking for a solution between x is equal to positive 1 and positive 2, you would just take the positive square root, and you get x is equal to the square root of 2, which is between 1 and 2. So as guaranteed by the intermediate value theorem, there is an input value between 1 and 2 for which the output will be equal to 0. So today we looked at the intermediate value theorem. We understand that the intermediate value theorem can be used when the hypotheses are satisfied. We understand that the intermediate value theorem is an existence theorem. If the hypotheses are satisfied, it tells us the existence of an input value between a and b at which the output value will be equal to y from the hypotheses. And then we also looked at a particular application of the intermediate value theorem to determine whether a function will have at least one zero on a given interval of x values. And that can be done as long as you have an interval ab, and f of a is either positive or negative, and f of b would have the opposite sign.